Imagine falling into a black hole, not observing one from a safe distance, not reading about one in a textbook, actually falling in, feet first, conscious, aware of everything happening to your body and to the universe around you as you cross the most terrifying boundary in physics. What would you see? What would you feel? And what is actually in there, behind the curtain of the event horizon, in the one place in the universe from which no information can ever return? The honest answer is we do not know. Nobody has ever been inside a black hole. No probe has ever returned. No signal has ever escaped. The interior of a black hole is, by definition, the only place in the universe that is permanently, absolutely hidden from us. But we are not completely blind. General relativity, Einstein's theory of gravity, makes very specific predictions about what happens inside. Quantum mechanics offers competing and contradictory predictions, and the conflict between these two theories, the two most successful theories in the history of physics, reaches its most violent peak inside a black hole. Whatever is in there is not just unknown, it might be the key to unifying all of physics. Let us start the journey. You are floating in space, a safe distance from a supermassive black hole. From here, it looks exactly as its name suggests, a black sphere, a perfect circle of absolute darkness, surrounded by a thin, bright ring of light. That ring is the photon sphere, a region where gravity is so strong that light itself is bent into orbit around the black hole. Photons circle endlessly, trapped in a gravitational prison, creating a halo of light around the darkness. Behind the photon sphere, you can see the distorted images of stars and galaxies on the far side. Their light has been bent around the black hole by gravity, warped and stretched into arcs and rings. This is gravitational lensing. The black hole does not just consume light, it bends the entire visible universe around itself, like a dark lens distorting everything behind it. And at the center, the dark circle, the shadow, the event horizon, the point of no return. I have stared at the Event Horizon Telescope image of M87's black hole for hours. That blurry orange ring around a dark center. It looks almost gentle, almost peaceful, but that dark center is the most violent, most extreme, most fundamentally unknowable place in the observable universe. And I think the contrast between how quiet it looks and how extreme it is might be the most unsettling thing about black holes. The event horizon is not a physical surface. There is no wall, no membrane, no barrier you can touch. It is a mathematical boundary defined by the Schwarzschild radius, the distance from the center at which the escape velocity equals the speed of light. If you are outside this radius, you can still escape. If you are inside, you cannot. Nothing can. Not light, not information, not you. The Schwarzschild radius depends on mass. For a black hole with 10 times the mass of the Sun, it is roughly 30 kilometers. For the supermassive black hole at the center of our galaxy, Sagittarius A star, with 4 million solar masses, it is about 12 million kilometers. And for M87 star, with 6.5 billion solar masses, it is roughly 20 billion kilometers, larger than our entire solar system. Now, you begin to fall. As you accelerate toward the black hole, the first thing you notice is not the gravity, it is the light. The universe in front of you, in the direction of the black hole, begins to compress. Stars that were spread across the sky squeeze together into a smaller and smaller circle ahead of you. Behind you, the opposite happens. Stars spread apart, thinning out, the sky behind you growing dark and empty. This is relativistic aberration, a consequence of your increasing speed. As you approach a significant fraction of the speed of light, the entire universe appears to concentrate into a bright circle ahead and a void behind. You are falling into a tunnel of light surrounded by growing darkness. The colors change too. Stars ahead of you shift toward blue as their light is compressed by your motion toward them. Stars behind shift toward red and then infrared, disappearing from visible light entirely. The cosmic microwave background itself, normally invisible, shifts into the visible spectrum ahead of you, briefly appearing as a faint glow before shifting further into ultraviolet and X-rays. You are seeing radiation that has been traveling since the universe was 380,000 years old, made visible by your velocity. What happens next depends on the size of the black hole, and this is something most people do not realize. Not all black holes are equally dangerous at the event horizon. If the black hole is small, a stellar mass black hole with perhaps 10 times the mass of the Sun, you are dead long before you reach the event horizon. The tidal forces, the difference in gravitational pull between your feet and your head, becomes so extreme that your body is stretched vertically and compressed horizontally. This is called spaghettification. It is not a metaphor. Your body is literally pulled into a long, thin strand of matter, like a noodle, miles long and atoms wide. You are torn apart, molecule by molecule, atom by atom, long before you cross the boundary. But if the black hole is supermassive, millions or billions of times the mass of the Sun, something very different happens. The event horizon is so far from the center that the tidal forces at the boundary are surprisingly gentle. You could cross the event horizon of a supermassive black hole and feel nothing. No pain, no stretching, no warning. You would not even know you had crossed it. The most dangerous boundary in the universe is invisible and imperceptible. And this is one of the details about black holes that haunts me. There is no sign, no alarm, no flash of light. One moment you are in a universe where escape is possible. The next moment you are in a universe where it is not. And nothing about your immediate experience tells you the difference. The trap does not look like a trap. The door does not look like a door. You only realize you are imprisoned when you try to leave and discover that leaving is no longer a concept that applies to you. But someone watching you from outside would see something entirely different. And this is where black holes start to warp not just space, but time itself. To an outside observer watching you fall toward the event horizon, you appear to slow down. As you approach the horizon, your image gets dimmer and redder. Light from your body is being stretched by the intense gravity, its wavelength increasing, shifting from visible light to infrared to radio waves to wavelengths too long to detect. Your clock, as seen by the outside observer, appears to tick more and more slowly. At the event horizon, from the outside perspective, your clock stops entirely. You appear to freeze at the boundary, growing dimmer and redder, never quite crossing, fading from view over what appears to be an infinite amount of time. From the outside, you never enter the black hole. You are frozen on the surface forever, gradually fading to invisible. But from your perspective, nothing unusual happens. You fall through the horizon in finite time. Your watch ticks normally. Your experience is continuous and uninterrupted. The event horizon passes you by like an invisible line drawn in empty space. Both perspectives are correct. This is not a trick or a paradox. This is what general relativity predicts and what all observations confirm. Time passes at different rates depending on the strength of gravity. Near the event horizon, the difference between your time and the outside observer's time becomes infinite. You and the outside universe literally experience different amounts of time passing. And I think this is the most profound thing about black holes, more profound than the darkness or the density or the destruction. They break the assumption that we all share the same time. Inside and outside a black hole are not just places, they are different timelines, different rates of reality. The universe outside ages billions of years while you fall for what feels like minutes. The friends you left behind grow old, die, and are forgotten, while you are still falling, still conscious, still counting seconds on a watch that tells the right time in the wrong universe. Now you are inside. You have crossed the event horizon. What is in here? This is where physics gets truly strange. Inside a black hole, according to general relativity, the roles of space and time switch. Outside the horizon, you can move freely in space, but are carried forward in time. Inside the horizon, you can move freely in time, but are carried inevitably in space, toward the singularity. The singularity is no longer a place, it is a moment in your future. You cannot avoid it any more than you can avoid next Tuesday. It is not somewhere you are heading, it is when you are heading. Every direction you look inside the black hole points toward the singularity. There is no direction you can travel to move away from it. Even turning around and firing the most powerful rocket imaginable would only change when you reach the singularity, not whether you reach it. The singularity is your future, and the future always arrives. As you fall deeper, the tidal forces increase, even in a supermassive black hole. The spaghettification that was gentle at the horizon becomes extreme near the center. Your body stretches, your atoms separate. The electromagnetic forces holding your molecules together are overwhelmed by the tidal gradient of gravity. You are disassembled, not by violence, but by geometry. The shape of space-time itself pulls you apart. And as the density approaches infinity, every physical theory we have stops working. The singularity, the heart of the black hole, the place where general relativity predicts a point of infinite density. All the mass of the black hole compressed into a region with zero volume. Density, temperature, and the curvature of space-time all become infinite. The equations produce infinity, and infinity is not an answer, it is a confession. It means the theory has been pushed beyond its limits. The mathematics is screaming that something is wrong with our understanding. Nobody actually believes there is a point of infinite density at the center of a black hole. What physicists believe is that general relativity is incomplete. At the extreme conditions near the singularity, quantum effects become dominant, and a theory of quantum gravity, a theory we do not yet have, is needed to describe what really happens. And this is where the real mystery begins, because the theories that attempt to describe the singularity disagree with each other in spectacular ways. In classical general relativity, the singularity is a point. All paths lead to it. All matter is crushed into it. It is the end of the road for anything that enters the black hole. But in loop quantum gravity, one of the leading candidates for a quantum theory of gravity, the singularity does not exist. Quantum effects create a repulsive force at extreme densities that prevents matter from collapsing to a point. Instead of a singularity, there might be a region of extremely high but finite density, a quantum core. The black hole is not a bottomless pit, it has a floor. In string theory, another leading candidate, the singularity is replaced by a structure called a fuzzball. According to this model, a black hole is not empty space with a singularity at the center. It is a tangled ball of quantum strings filling the entire volume inside the event horizon. There is no empty interior, no void to fall through. The entire black hole is a solid quantum object with no singularity at all. And then there is the firewall hypothesis. In 2012, physicists Ahmed Almeri, Donald Marloff, Joseph Polchinski, and James Sully proposed that the event horizon might not be the smooth, invisible boundary that general relativity predicts. Instead, quantum effects might create a wall of high-energy particles at the horizon, a firewall that would incinerate anything that crosses it. In this model, you would not fall peacefully through the event horizon. You would be burned to a crisp the moment you touched it. There is no interior to explore because you never make it inside. I find the firewall hypothesis genuinely disturbing, not because it predicts destruction. Spaghettification already does that, but because it suggests that our picture of smooth, continuous space-time might be wrong at the most fundamental level. That the event horizon, which general relativity says is nothing special, is actually a violent quantum boundary. That the two pillars of physics, relativity and quantum mechanics, are so incompatible that they cannot even agree on what happens at the door, let alone what is inside the room. And there is one more possibility that I cannot stop thinking about. What if the singularity at the center of a black hole is not an end, but a beginning? Some cosmologists have proposed that the collapse of matter inside a black hole might trigger a new Big Bang on the other side, a new expanding universe born from the singularity of a black hole, inaccessible from our cosmos, with its own space, its own time, its own physics. In this picture, every black hole is a portal to a new universe, and our own universe might have been born from the singularity of a black hole in some parent cosmos. There is also the question of rotation. Almost every real black hole in the universe is spinning, and a spinning black hole, described by the Kerr metric rather than the Schwarzschild metric, has a very different interior structure. Instead of a point singularity, a spinning black hole has a ring singularity, a one-dimensional ring of infinite density. And some solutions to the Kerr equations suggest that passing through the ring rather than hitting it could lead to other regions of space-time, perhaps even other universes. The mathematics allows it. The physics is uncertain. And the practical reality is that any matter approaching the ring singularity would be torn apart and scattered by the chaotic oscillations of space-time that Roger Penrose and others showed must exist near the center of any real perturbed black hole. This is highly speculative. There is no direct evidence for any of it. But it is mathematically consistent, and it connects to ideas from loop quantum gravity, where the singularity bounces rather than collapses. And if it is true, the universe is not just bigger than we think, it is deeper. A nested structure of universes within universes, each one born from the heart of a black hole in the one above it, a cosmic family tree stretching back to origins we cannot trace. Now, you might ask, if no information can escape a black hole, how can we ever know what is inside? And this question leads to what Stephen Hawking called the greatest crisis in theoretical physics, the black hole information paradox. In 1974, Hawking showed that black holes emit radiation and slowly evaporate, but that radiation appears to be random, carrying no information about what fell in. If the black hole eventually evaporates completely, the information about everything it consumed appears to be permanently destroyed. But quantum mechanics says information can never be destroyed. It can be scrambled, hidden, made impractical to recover, but never truly erased. So, which is right? Does the black hole destroy information, violating quantum mechanics, or does the information somehow escape, violating general relativity? For decades, this paradox was considered unsolvable. In 2019, physicists made a breakthrough. Using a concept from quantum information theory called the island formula, they showed mathematically that information is not destroyed. It is encoded in subtle quantum correlations in the Hawking radiation itself. The information comes out, but in a form so scrambled that reconstructing it would require capturing and analyzing every single photon of Hawking radiation emitted over the entire lifetime of the black hole. The information is preserved, but functionally irretrievable. The universe keeps its records, but it writes them in a code that might take longer than the age of the universe to decode. In 2022, physicists Xavier Palmet and Stephen Hsu published a series of papers proposing that information is encoded in the quantum state of the gravitational field outside the black hole and imprinted in the Hawking radiation. According to their work, the information is fully available to an outside observer, at least in principle. The black hole does not destroy information, it encrypts it. And I think this is a metaphor for the entire subject. Black holes do not give up their secrets easily. They do not destroy the truth. They encrypt it. They hide it behind event horizons and singularities and quantum scrambling so thorough that recovering it may be impossible in practice, even if it is possible in theory. The universe is honest, but it speaks in a language we have not yet learned. We cannot go inside a black hole. We cannot send a probe. We cannot receive a message from anyone who crosses the event horizon. The interior of a black hole is the one place in the universe that is permanently beyond observation. But we are not helpless. The Event Horizon Telescope has already imaged the shadows of two supermassive black holes, M87 star and Sagittarius A star. These images, produced by linking radio telescopes across the entire planet into a single Earth-sized virtual instrument, show the dark shadows surrounded by glowing rings of superheated gas orbiting at nearly the speed of light. They are the closest we have ever come to seeing the boundary between the known and the unknown. Gravitational wave observatories like LIGO and Virgo detect the ripples in space-time produced by black hole mergers, giving us information about their masses, spins, and collision dynamics. Every gravitational wave detection is a message from the most extreme events in the universe, two black holes spiraling together and merging in a fraction of a second, releasing more energy than all the stars in the observable universe combined. These signals tell us about the exterior of black holes with extraordinary precision, but the interior remains hidden. The next generation of instruments will push further. The space-based gravitational wave observatory LISA, planned for the 2030s, will detect mergers involving supermassive black holes. The next generation Event Horizon telescope will produce sharper images, potentially revealing the structure of the photon ring in enough detail to test predictions of general relativity near the horizon. And advances in quantum computing may eventually make it possible to simulate the quantum gravitational conditions near a singularity, giving us a theoretical window into a place we can never physically visit. And this is what I keep coming back to. The fact that we can say anything at all about the interior of a black hole is extraordinary. That a species of primate on a small planet has deduced through pure mathematics and indirect observation that objects exist in the universe from which light cannot escape, that time and space switch roles inside them, that their centers contain something so extreme that our best theories break down, that we can argue about whether the interior is empty or a fuzzball or a firewall or a portal to another universe. All of this from a planet that cannot even see inside. Maybe one day a theory of quantum gravity will tell us what replaces the singularity. Maybe it is a quantum core. Maybe it is a fuzzball. Maybe it is the seed of a new universe. Maybe it is something no one has imagined yet. But right now, in 2026, the interior of a black hole remains the deepest mystery in physics, a place predicted by our best theory, forbidden by our best observations, and hiding somewhere in its heart the answer to how gravity and quantum mechanics fit together. The universe has many secrets, but this one is locked behind a door that only opens inward. If this video changed how you think about reality, hit subscribe. We ask the questions that keep you up at night every single week. Next time, are we alone in the universe? What the Fermi paradox really means. See you there.